Hi there, Turgeon here, bringing you physics from afar. The big questions in this unit relate back to electricity, but more specifically, they relate to charges. Charges and how they move, how they behave, what are the forces. When we thought about stuff like the balloon sticking to the wall, it made sense to talk about charges that were kind of static or stationary. Now it makes more sense to talk about charges that are moving. Big question, how do they move? We learned about Ohm's law. Ohm's law kind of answers the question how they move because it says, well, there's a voltage. It's kind of like a pressure. But wait, that's mediated, that's mitigated, that's slowed down by the resistance. Now I want you to think more specifically about these circuits. You might have taken apart some electronic device and seen these circuit boards like this. It looks like this confusing array, but what I'm going to show you today actually forms the basis. There's some fundamental laws. There's some rules behind how all circuits operate. Basically, it comes down to series and parallel. It has to do with how you make these connections between the resistors or the loads, the load or the resistor. A series circuit is a way of connecting the resistors so that they're all on one single path. There could be multiple different paths within a circuit, but a series circuit has something that looks like this. You have a resistor or a load, and then you have multiple resistors, but they are connected all together. You can see that the voltage has more work to do, literally work, in the energy that it expends to push electrons through these resistors. The equivalent resistance, also known as the total resistance, is just adding those up. So if this was 10 and 20 and 20, then the equivalent resistance would be 50 ohms, 10 plus 20 plus 20. Another interesting fact, which we'll explore more through simulators and hopefully through some lab investigations, is that the current is the same through every single resistor. So if you change this resistor that I said was going to be 20, if you change that to 50, it slows the current down there, but it actually slows the current down everywhere. Back to the garden hose analogy, I remember using the hose when I was a kid, and my older brothers would do this infuriating thing where they put a kink in the hose, and the kink in the hose slows down the flow of the water, obviously, but it slows down the flow instantaneously everywhere from the faucet where it's connected to the house all the way to the end. And now I have no flow through the hose because my brother is putting a kink in the hose, much to his delight and my frustration. The voltage is the energy. So let's say this was 100 volts. That 100 volts would be split among those three resistors. Let's look at an example. So let's say I have this, every one of these resistors is 11 ohms, and I want to figure out the current and voltage for every single resistor. So what I'm going to do is first identify the equivalent resistance. Write down in the margin of your notes, this is a really, really good thing to figure out. You want to know the equivalent resistance of the whole circuit if possible. So I know the current's going to flow from this positive end with conventional current, but it's kind of a question of how much is going to flow. So then I can take my total equivalent resistance and divide it into the total voltage using Ohm's law. This is the voltage of the entire circuit, 12 volts. I'm going to use Ohm's law. I've written out the quotient form of it, I equals V over R. You could also write V equals IR. 12 over 33, that's 0.36 amps. And we know that the current is going to be the same everywhere for a series circuit. Can't say that often enough. The current will be the same everywhere. Now, as I'm doing this, I'm realizing that there might be a misconception. I'm about to label this 0.36 amps on every single resistor, and you might think that that's because they're all 11 ohms. Even if they weren't 11 ohms, you would have a different value, but if they were all different, they are still all going to have the same current through them. So it's 0.36 amps through every single resistor. There's also a total current of 0.36 amps. It's the total, and it's the same everywhere. It's shared by everything. It's also the amount of current coming back to the battery right here. Now, the next question is, what about the voltage? Well, the voltage is split evenly. The voltage is split from 12 volts. Each of these will get 4 volts because they are equivalent resistors. I don't want to get too much more into that. I'm just going to say I'll probably typically give you 3. If I ask you about the voltage, I'll ask you about 3 equivalent resistors, probably. But if you did want to figure out, let's say it was instead of 11, 11, 11, if it was 20 and 30 and 11, then what you would do is you'd have a new total resistance. You would figure out a new current, and then we could use Ohm's law individually for each resistor. So we used Ohm's law for the whole circuit. You're also allowed to use it individually for each resistor. So to summarize, the current's the same everywhere. The voltage is split up and adds up to the total voltage. The total current is the same as the current through every single resistor. Parallel circuits. Here's a parallel circuit. A parallel circuit, I like to think of it as you've constructed it by starting with a really simple circuit, then you added another path that's still directly connected to the battery, and then another path that's still, or it doesn't have to be 3, it could be 2 or 5 or 50, but you're adding additional paths that are still connected directly to the battery. Now, I want you to convince yourself of that. I want you to look at this and say to yourself, do I realize that this 10 ohm resistor is directly connected to the battery? Here's a conductor, and conductors provide instantaneous connection. If I go like this, it makes it a little more obvious that this resistor is connected directly to the battery. Sorry, it's not lining up perfectly, but you get the idea. Kind of want now I want to make that line up. Now I'm determined. Let's see if I can get a little bit more of a fine-tuned rotation here. Now I'm satisfied. So it looks more like it's connected directly to the battery. The battery is the voltage source. It might not technically be a battery. It could be something like an outlet. So these have multiple paths. There are 3 of them. The current goes here and it flows through here. It also goes here and it flows through here. The current's actually going to have to split up. Like if it was 100 amps coming out of here, it's going to split through these and then reconvene coming back. Let me say that again. If it were 100 amperes, that's a lot of current, by the way, then it would have to split through here and through here and through here. So a parallel circuit is a connection with multiple paths. Every resistor has the same voltage because they are directly connected to the voltage source. The current is not the same. It gets split up among the resistors. The total resistance is less than the smallest. Wait, how's that possible? What ends up happening is, if I have this connected, and let's say this is 12 volts. 12 volts divided by 4, that's 3 amperes. Now when I add this resistor, this is, by the way, the hardest concept to understand in all of circuits. I add this resistor, what ends up happening is I also now have, if this was 12 volts, now this is going to be 1.2 amps. I know I'm doing a lot of math in my head, but I'm just using Ohm's law. You could pause the video and let me, you could rewind and you can hear me explain that again. But this is 3 amps. This is 1.2 amps. That's more current flowing when we added this resistor. Again, this is just 3 amps. Now it's 4.2 amps because I added 1.2 amps. That is the equivalent of a lower resistance. If these were 2 equal resistors, then the total resistance would be cut in half. These are not equal resistors, so that law is not true, but that is a useful law right there. I'm going to make a grocery store analogy. So let's say you have 2 cashiers, and these are supposed to be grocery carts. You have people lining up at the grocery store. Now another cashier is going to open here at this other register, but wait a second. This cashier is going to be slower than the other 2. Will that help the flow of people out of the grocery store? Yes, it will. Any additional path decreases your resistance to getting out of the grocery store. Any additional path increases the flow of people out of the grocery store. Any additional path is still an additional path, even if it's 30 ohms. The overall effect is that there's less resistance because there's more current flowing. let's do an example. Here's my parallel circuit. I have 6 volts, I have 10 ohms, and I have another 10 ohms. So the current and voltage for each resistor. For one resistor, they're identical. The voltage is 6 volts because they're both connected directly. The resistance is 10, so the current is 0.6 amps. So I have 0.6 amps flowing right here, 0.6 amps flowing right here. The total current, by the way, is 1.2 amps because you can add them up. I don't know if I asked for that. So the current for this resistor is 0.6 amps. The current for this resistor is 0.6 amps. The voltage for this is 6 volts, and the voltage for this is also 6 volts. The equivalent resistance of the whole circuit is 5 ohms, using the rule I just said, where they're both equal. But what you can also do, if you didn't remember that rule, you could use the total voltage and the total current to calculate the total resistance using Ohm's law, VIR. So the equivalent resistance is 5, and the quick way is also getting you 5 ohms. Now I want you to, we can sort of summarize this. I shouldn't have called this so. In years past, I did this as a warm-up. But let's summarize. Think about what you could say. What's like a way to describe? And you're going to pause the video in a second. Write this table down and think like, what words could I put in here to summarize voltage and current in series and parallel? Pause the video because here comes the answer. Here it comes, 3, 2, 1. Now, in the words of previous students, in the handwriting and words of previous students, voltage splits in series, current splits in parallel. The equivalent resistance for series is if you add resistors, it gets greater. But in parallel, if you plus R, add resistors, it gets less. So to summarize, charge moves differently in different types of circuits. In a series circuit, charge moves equally everywhere, and there will be different energy usages because of that charge through different resistors. In parallel, the charge does not move equally everywhere because the different resistors allow different amounts of charge to flow through them, but they will be they will be building off of the same energy source of the battery. This has been Physics from Afar.